Okay. Hi, hello. I'm gonna start talking because it's 8:30 and I like to talk. The QR code for attendance is up here today. In it, there's a pop quiz of functional groups. I ask a tricky, hard functional group question. Try to see if you can get it.
Is it the one like in the middle of the QR code?
No, it's on the form. Like there's a question on the Google form. I'll
Is
make
it
it.
really a pop quiz if it's an optional form and an optional section?
But on the form, it's a required question. Yeah, yes. And then does someone see on the form what's the like last like little optional question, the kind of bonus question for today?
Oh, song of the summer.
Song of the summer. Hey,
What's your song?
actually write down. You'll see later. Write down what you think the song of the summer is. Anyone who submits a song of the summer, I'm gonna make a Spotify playlist. I will send it out to everyone who contributes.
Okay, got it.
Let's see. Hey everyone, welcome in. Just scan the QR code. So, logistics-wise, we have section today over yesterday's lecture. Tonight, I'm going to be sending out a scary announcement. I'm so sorry. It's a little scary because it's about logistics with the exam, and it's a little intense. I know it's intense. So, just know I know that. Just know that it's coming from a place of love. But it is a little scary. I have all the problem sets, so that's good. Then for section tomorrow. So tomorrow's going to be a rough day, especially for Thursday lab folks. We have lecture 8:30 to 11:30. If you have Thursday lab, you have lab 1 to 5. And then sections are going to be in the evening tomorrow. And I will double check the room. Logan emailed me about it like last night. I think it's going to be in here. There will be a announcement about it. No, actually. So it's going to be on the first floor, Science Center 116. That's going to go on an announcement, though, so you'll see it. There's going to be a 4:30 section and a 6:30 section, but it is a pretty small classroom. So if you are a Tuesday lab person, you've already done your lab for the week, please try to come to the 4:30 unless you have like a hard conflict, just because otherwise there will be too many people in the 6:31 with all the Thursday lab folks. Also, tomorrow in lecture, we are going to hand out printed versions of the practice exams. You're going to be given 2 practice exams for the real exam. I'm going to have everyone kind of pick it up. I do think even if you're a tablet user, get a printed copy because your exam is going to be printed on paper. And sometimes some students in the class, their first time writing molecules on paper is on the exam. And it's just a little bit different. And like you just need to like practice doing it out by hand. I will say do not look at the practice exams until you are done with problem set 2, because that's going to be your number 1 priority right now. Are there any logistical questions before we start to jump into things today? And for the folks that just came in, just scan the QR code for attendance things. So, if I was in your shoes, I would feel pretty stressed after yesterday. Yesterday was very much the drinking from a fire hydrant kind of feeling of there was a lot of information very quickly. It was very new. And I could really see on people's faces at a certain point in lecture, it was just the lights were on, but no one was home. Like
after 10:45, just like.
Yeah. Like, and so I assume that it was a bit much, and today we're trying to kind of pick up the pieces of that. But a lot of it is in lecture 3, you saw for the first time what kind of the rest of the course is going to be like in terms of reactions. Like, you have never been given reactions to learn like this before. And I think a lot of the challenge of learning reactions is it's very visual. Like, it's a lot of like arrows and structures. And that kind of visual information, y'all don't have a lot of experience learning how to study or like how to internalize it. Like for a biology class, learning vocab, sure, you all have that down. For a Gen Chem class, doing like algorithmic math problems, y'all have down. But like, how would you go and memorize a bunch of visual information like this? And so a good like half or so of section today is going to be devoted to how we study reactions. And it's the first part of my 3-part series on how to study reactions that will pop up later in sections as we go throughout the course. Then after that, we'll touch on some of the reaction families that we talked about in lecture. But that is the game plan for today. Cool. Any last questions before we like fully jump in? Okay. So, first off, in order to know like how to study reactions, you should know how you're going to be tested on them. And Logan talked a little bit about this when he was like introducing the reactions, but I want to talk about it a little bit more explicitly and connect that to pages of your exam that you're going to see next week. So let's start off here with the anatomy of a line reaction. So a line reaction, we're going to have some starting molecule listed. Then we'll have an arrow, and we'll put other reagents, solvents, reaction conditions, and then we will have a product molecule on the other side. We call it a line reaction because it all fits on one line. And this will typically be given at the top of the page anytime you're learning a new reaction. And then you have all like the curved arrow mechanism stuff below it. But this is kind of a concise way of like presenting the reaction, the major transformation. So a line reaction makes really great problems on exams that we typically call box problems. So the way we write box problems is we take a line reaction and put a big box over one of the three components. So the classic example is we give you the starting molecule and reagents and we say, write what the product is. We could also put it over the reagents on the arrow and ask you to supply the reagents. And the kind of harder one to do is to ask you to predict a starting material given a product and some reagents. And so we're really making you think about it from several different vantage points here, but all of it is testing you on the same basic information of the line reactions. And you can see also on this, we can combine several reactions. Like this has a thiolate addition and a Grignard together. So like you could have up to, I think, 4 or even sometimes I've seen 5 steps on line reaction box problems. But one page of your 9-page exam will be box problems, just like this. Cool. So one thing to think about here with box problems, if you're going to have a page that has like 4 or 5 of these on there, do you think it's going to be an effective use of your exam time to write out a full curved arrow mechanism in order to get this answer? Based on how I asked that, no. Yeah, so we're going to have to keep that in mind when we're studying of like, we want, yes, to know the full mechanism, but we also want shortcuts to just be able to write what the product is going to be. Because all that we are grading in a box problem question is what is in the box of the actual structure. Like there is no credit that's given for showing your thinking on the side, or like if you show the thinking and almost get to the product but don't have it. It's like all based on the product of the reagents. So this is one of the 3 main types of questions that we can ask about reactions, box problems. Another main type is mechanism questions, and these are pretty kind of self-explanatory. Will be like, provide the complete curved arrow mechanism for the following transformation. And typically we will give you a full line reaction. With this, we want all of the arrows. All of the arrows need to be really specific. Like if you have like SME minus here attacking the carbonyl, you need to show specifically that your arrow is going from the lone pair on the sulfur and attacking this carbon. If your arrow was something like that, here, it's not clear where this is starting, right? Like even if I put the minus here, it's like you're, yes, having this molecule join there, but every time you're doing a curved arrow, you're presenting an argument for how you think this molecule is reacting. And like here, this is like in the bond area, but it's not a specific target of the carbon. So like that arrow that I just drew would get no credit. Whereas this, if you draw the arrow from the lone pair and specifically go to the carbon, that's what's going to get you credit. We could also, for full arrow, full mechanism questions, ask you about like HOMO-LUMO interactions, donor acceptor orbitals, things like that. So it is the most detailed way we can ask you about a reaction. Now, these show up on exams in kind of 2 flavors. The first is a known mechanism question. And a known mechanism question is basically like regurgitate the mechanism, like that you've seen in lecture. And the only way that we can really make a known mechanism harder is we can like stack multiple reactions. Like again, this one has the thiolate and then it has the Grignard. And so by doing multiple reactions in a row, even though they're just the arrows that you saw in the lecture notes, it's a little bit more challenging. Other things that we can do to make a known mechanism more challenging is we could start from an intermediate, like halfway through a reaction or something, or we could make you go backwards on a reaction if it was reversible. But all of these will be arrows that you 100% have seen before in lecture and drawn. The other type of question is a new mechanism question. Now, it's not going to be something crazy out of left field that you've never seen before. it's going to be very, very similar to a reaction that you have seen with maybe one wonky step. And the one wonky step has to at least be similar to what you have seen. Otherwise, it's not a fair question. So you're going to get an example of like a new mechanism question in one of the challenge problems where it's something that you haven't directly seen, but it's closely related in logic. And I know for sure a known mechanism is going to be one of the 9 pages, but we could split that page up into like half of it's a known mechanism, half of it's new, or this new mechanism could be like a part of another page. But typically we've done like 1 page of the 9 is mechanism. Any questions on mechanism questions? Okay, the last one's the scariest. Synthesis questions. So, what we will give you for a synthesis question, we will give you a starting molecule, we will give you a product molecule, and we will say something in the instructions like in 10 or fewer reactions, form the product from the starting material. So this is one that you do not have all the reactions to do yet. So like this is one that would be an exam 2 synthesis question. But what you have to do is you have to use the reactions that you have learned and put them together in the right order and generate the intermediates in order to actually create the product. So it's a lot of like higher order thinking. And like if you think about like that hierarchy of learning, like, you know, the bottom level is like regurgitate or something, or like just understand, analyze, evaluate. The highest level on there is create. And a synthesis question really makes you think at this highest level. So you have to know these reactions, not just from the curved arrow standpoint, but there has to be some higher order thinking going on in order to think about selectively, why would I use this reaction? In what context? What's its purpose? So a few things with synthesis questions. You're going to see some practice on the problem set. You're also going to have a practice on each of the practice exams as well. The synthesis on the first exam will be the last page. It's only 1 synthesis question, and it probably will not be more than like 6 steps, 6, maybe 7 max. Whereas like exam 2, it could be like 10 or 11 steps. So it is a lot. For synthesis questions, there should be no curved arrows. You are not showing mechanisms for anything. All you are doing is line reactions. So like the purpose of this line reaction is to add a bromine on a benzene. The purpose of this one is to make it into a Grignard. And the only things that we are grading you on the reagents, and we are grading you on the structure. And we try to give partial credit as we can. There are often like multiple ways that you can get to the product, and if your way is like chemically valid and it's not what our answer key is, you will still get credit. But this, I would say, is the most challenging thing we will ask you in this course, just in terms of like thinking and putting it all together. Any questions about synthesis? Okay. So again, I'm just kind of laying it out here of how you are going to be tested, and that's going to inform kind of our study approach of how we are going to kind of internalize these reactions. But before I get into the approach, just some general advice. So one thing I'm guilty of in a class, like when I am a student, is I don't like working on the homework until I've already studied the class notes. Like I've done my little system, I've made my little aesthetic notes, I've highlighted all the terms and everything. I feel really competent about the material. And then I'm like, okay, I can do the homework. And it makes it easier to do the homework once you fully studied and everything, right? You simply don't have time for that this summer. Like, you have to be working practice problems while you are still learning and integrating this information. And I would say, more than that, using the practice problems as part of your learning process. Do not expect to go into the problem set knowing what to do. Expect the problem set to be your chance for integrating it and starting to learn it. So just getting out that disclaimer of you can't like wait to do practice later. Do it as you go. The biggest challenge for students in organic chemistry, full stop, is how long does it take you to integrate a new set of reactions? Because lecture 4, we're doing stereochemistry, which is kind of a one-off thing. But after that, every lecture to the end of the course, we are just going to be giving you 8 to 10 more reactions. And so this skill of being handed a batch of reactions and figuring out how to internalize them so that you can do these even like higher level synthesis questions, that is like the rate limiting step for your success in this class. It is like, how quickly can you take in this information, internalize it. And so one thing that you're going to see, and that I see every year with students, is you are going to have to adapt your study methods. If something is taking too long, you need to abandon it and regroup in another strategy. I am like happy to talk with you about study things as like how they are going and what is working with you and what is not. But like there isn't a ton of time to pivot, like to like let it go on like a month or something. Like it needs to be pretty quick, like honest conversations with yourself about how the studying is working. Because again, I will fully say, I like studying that feels good. I like studying where I generate pretty things and where I feel smart. And a lot of what we are asking you to do in this course, because of the pace of it, is it's going to feel a little overwhelming. It's not going to feel like you have a full handle on it. And also you're not going to be able to study in the way that's the most comfortable. So I like to give that disclaimer. Yeah. A metaphor that I really like about reactions is like, think about reactions as tools in a toolbox. Like they all accomplish certain chemical goals. And between a toolbox that is messy and disorganized and a toolbox that is very organized and has a bunch of compartments, which is the toolbox that you would like to use? The organized one, yes. And so I think another big challenge here is like, how do you organize all of the reactions that we teach you? And the main strategy that I'm going to talk about is reaction families. So there are certain families of molecules that react very similarly. And like for lecture 3 yesterday, I group it into about 3 families of reactions. And that's kind of like your little dividers in the toolkit. That's going to help you just kind of mentally organize it, because at least yesterday in lecture, it probably felt like a sea of just information with no clear discernible pattern. So that is my like intro general advice. Are we ready to see the like study method? Okay. So it's not a groundbreaking idea, but in order to effectively learn reactions, you need to study them at different levels of detail. And you need to do those different levels of detail kind of concurrently when you're studying. So the most detailed level that you can study a reaction is the full curved arrow mechanism, like going through each of the arrows and understanding why it's there, the HOMO, LUMO, and everything. But if you only study that way, it's a bottoms-up approach where you might not get to the higher order thinking of being able to like use that information as synthesis. You might be able to draw every curved arrow, but not think about how to like sequence different reactions to create something. And so this needs to be part of your studying, but it cannot be the only thing. And it cannot be like the you do this first and then do other things. It really needs to be just part of it. The second level up from the full curved arrow mechanism is mechanistic logic. So when you are going through a new reaction, one thing I would highly recommend doing is for each sub-step of the reaction, translate it into plain English, literal like words, because y'all are used to studying words and like getting it out of the visual information sphere is something that's helpful to do. So we're going to practice this with the most complicated reaction that y'all saw yesterday, which is the acetal formation reaction. So in the section notes, I printed it out here with the arrows. If you are not a tablet user, I would recommend getting out your lecture notes from yesterday and going to the page that has the acetal reaction. And if they do get out the lecture notes, if you can like call out whatever that page number is for other folks, that would be helpful.
It's page
56. Cool, thank you. Okay. So we're starting out with kind of what we give you in lecture, which we give you a line reaction and then the full curved arrow mechanism. And so let's, as a group together, go through and start thinking about the mechanistic logic here. So can someone give a suggestion for like what words would you use to describe this first sub-step? Protonation, yeah. And I'm going to say we're going to protonate the carbonyl. Easy. Now, harder question, the deeper level of detail. Why?
So that we can do a nucleophilic attack.
Yeah, why can't we just do a nucleophilic attack with like ethanol normally on the carbonyl? Why do we need to protonate it? Yeah. Not quite, but a great thought because that is the answer 80% of the time. Yes.
Because otherwise,
So it makes it more nucleophilic. Or, sorry, electrophilic.
Makes it more electrophilic. How does protonating a carbonyl make it a better electrophile?
Oh, because the oxygen has a positive formal charge, it's more.
Ding dong. So remember, we talked about in a reaction, we have like the HOMO and the LUMO, and we have this gap that they have to cross in order to actually react. So you can make a reaction go better by lowering the energy of the LUMO and then smaller gap between them, or you can raise the energy of the HOMO. In this molecule, the carbonyl is our electrophile, and it's the electrophile for most of the reactions that you learned yesterday. So the reason that we protonate it is to make the carbonyl a better electrophile by lowering the energy of the LUMO. And what orbital is the LUMO? Pi star CO. And again, it's lowering the energy of the LUMO because of our low energy trifecta of a positive formal charge is going to lower the energy of our orbital. Cool. So that is our first step. Second step, can we try to translate this into like plain English? So who wants to take a stab at like saying what's going on here? I feel like this half of the class has been quieter, so I'm going to get someone over here. Yeah. Yeah. And I'm going to make it even a little bit more specific. An alcohol nucleophile attacks a carbonyl electrophile. So yes, a nucleophile electrophile attack. And then I think specifying the functional groups is helpful because that's going to be our lens for looking at molecules. So what's our HOMO-LUMO interaction here? What's the HOMO? Yeah, so the lone pair on the oxygen. And then our LUMO, we said, is the pi star CO. Cool. Great. Step 3 over here. And I'm going to actually take these second two steps together. What we have is first we have a deprotonation, and then we have a protonation. Now, did Logan use this SOL abbreviation in class? Great. So it's just something in the solvent, and it's just, we don't care what it is. In this case, it's probably another HOET molecule that's going and grabbing it, but like we don't care. We're just calling it SOL. You're going to be able to use SOL on exams as well. So we have a deprotonation here, followed by a protonation. So I'm going to call that a proton transfer. And before we think about kind of why this step is happening, let's go ahead and look at the next step, and then we'll kind of circle back to kind of figure out the logic of why we did it. So 4. This step had a special name in lecture. Does anyone remember what we called this step? The lone pair push. Who was that? Oh, hi. Wait, is it Anna? Ding dong. With the earrings. Stunt. Okay, so we are going to lone pair push and kick off a water. So I'm just going to put lone pair push off water. What's our donor acceptor interaction for this? So where does our first arrow like start? What's our main donor? Another oxygen lone pair, great donor, trend alert. And then we're breaking a sigma CO. So what must our acceptor orbital have been? The antibond. If we broke a bond, we put electrons in the antibond. So sigma star CO. Great. So now, with this in mind, let's go back and look at this step. So this step, we removed a hydrogen on the OET thing, and then we added a hydrogen on the OH. Given that we are doing this lone pair push, why did we do this proton transfer? Yeah.
Because an alcohol group is a bad fusion group.
Yeah.
And
So, like, one part of it is we need to make the OH a better leaving group because we're kicking her off. And then, what about the OET side? If she has a positive formal charge, is she going to want to do a lone pair push? No, she has a positive formal charge. She said, I need more electrons. Why would I do a lone pair push and share it with another atom? So the second part is to set up for the lone pair push. And I don't know that like Logan adequately captured lone pair push. To me is a cinematic moment. It's the drama. It's the breaking point. It's the climax. It's 4 roommates sharing an apartment in Brooklyn, and Chelsea is like, "Water, I hate you. Get out!" and like pushes her out the door. It's the whole moment. And like we need to think about this as like narrative story. We're building up to something. The lone pair push is where the action drama happens. It is the only way we have seen to break a sigma bond that's not just acid-base protonation. She's powerful. Let's recognize her. So we've gone through these steps, and again, I combine these two in one to talk about the proton transfer for 3. So now, down here, how would we describe this step?
Nucleophilic attack of alcohol on the carbonyl.
Yes, and doesn't that look strangely similar to this? Couldn't we use the exact same description, exact same donor-acceptor interactions? In fact, I'm just going to straight up copy and paste and then replace the number. So alcohol nucleophile attacks the carbonyl electrophile, again, part 2, the remix. And again, so when you were studying it, looking for those little patterns and looking for the parallelism here is going to be helpful in order for this to seem like more common patterns and not all just distinct information for one thing. Okay, then we just have one last step. How would we describe it? Deprotonation, yeah. Why are we doing it?
Because it's a hemiacetal but can be acetal.
I mean, no, this is just a protonated acetal, yeah. So why did we deprotonate it?
So the carbon doesn't have a charge.
Yeah, to make it neutral. So we made it through the reaction. Do you see how at every step we had to understand what is happening and why it is happening? Those are the questions that you should be asking yourself, both when you learn a new reaction in lecture and when you go back and study this information. But even with this, it still feels a little abstract. Like we were in the weeds of it, so it's harder to see the big picture. But we have done kind of our most detailed level of analysis. Zooming out very slightly, one thing that I think is helpful then, and I pre-wrote this because just to save some time, is take your mechanistic logic that you wrote out for each of them and then write a little reaction summary where you just list out the steps, again, in the kind of plain English here. And now, for each of the steps that we did, I want us to classify them as either an acid-base step, a nucleophile attacking a carbonyl electrophile, or a lone pair push. So, on fingers, can you show me one step that's an acid-base step?
Step number 1.
On fingers, but yes, step number 1. And then there are a few more. So, on fingers, what's another step that's an acid-base step?
I can't show 6 with fingers.
Word. I appreciate y'all. I see. So we had 6, and then other people had 3. Our proton transfer is just a protonation, deprotonation together. So after like lecture 2 and problem set 1, y'all should be kind of pros at acid-base arrows. Like when I say like protonate an alcohol, you at this point should have kind of a mental image of, okay, the lone pair on the alcohol would go grab a hydrogen from something. And like that shouldn't be something that you're having to like think a lot about. It should be something that's kind of getting more and more automatic. Okay, then steps 2 and 5 are nucleophile attacking carbonyl electrophile. And we can, again, picture it in our heads of like, okay, it's a lone pair on the nucleophile attacking the base of the carbonyl, pushing up onto the oxygen. That's going to be the same every time. And then the only other type of arrows that we had was a lone pair push. And so, to be so honest, for all of lecture 3, and hence for all of the exam 1 content, these are the only 3 types of arrows you really learned. There's maybe one other one when we talked about conjugate addition with the enones that we'll get to, but like almost every arrow you drew yesterday is one of these. These are the valid moves that you have. Kind of like for resonance, we said that we could do like bond to lone pair, pi bond to pi bond, or lone pair to pi bond. Like these are the valid rules that you have right now for the reactions that we're asking you now. Cool. So that kind of completes levels 1 and 2. Let's start zooming out even more, and let's think about studying the line reaction. Like we said for our box problems, we just need to be able sometimes to write a structure, and we don't want to have to think about the full mechanism to get there. And so one tool that I think is really helpful is what I call a fake mechanism. So a fake mechanism is literally drawing instructions as if you're talking to someone who is not in organic chemistry. Like, call a friend, be like, hey, I want you to look at this molecule and I'm going to tell you, erase this, draw this, put line here. Like, truly smooth brain energy is the fake mechanism, but it is a helpful tool in order to be able to answer truly 1/9 of your exam. So let's look at this. The other thing at the line reaction level that I think is really helpful is functional group analysis. So what functional group do we have here? Alcohol. Good. What functional group do we have here? Aldehyde. And this one can also happen with a ketone, so I'm going to put aldehyde or ketone here. And then what functional group do we have in the product? Acetal. And then we have an acid catalyst. Okay. So a fake mechanism for this, if I had to come up with drawing instructions for my friend, I was about to be like, most of my friends know organic chemistry, which is sad. A lot of them are like in med school right now, so like it's been a minute, but I'd say fully erase the carbonyl. So that's step 1. So we are erasing the carbonyl. And then to get to the product over here, we essentially need to add on 2 bonds to our OET. And remember, this can be for any alcohol. This specific reaction was ethanol, but we could do it with methanol or phenol or like name your alcohol. So I'm just going to call this ROH, just generally. So I'm going to say, as the second step in the fake mechanism, is add 2 OR in its place. So again, fake mechanism would be erase the carbonyl, add 2 ORs in its place. And that does get us to the product, correct? Okay. So for this reaction here, I want you to take a second and try to just draw the product. Not thinking through the full curved arrow mechanism. Try using your fake mechanism here in order to just draw what the product of this reaction should be. I'm going to give you like 20 seconds. So first step is I erase the carbonyl. I just have a naked little hexagon over here. And then I look at my OR group. So it's going to be O, and then we have 1, 2, 3 carbons. So I'm going to add 2 of those, O, with 1, 2, 3 carbons. 1, 2, 3 carbons. That's the product. So much faster than thinking through the full curved arrow mechanism. Will be necessary for the box problem page. Any questions on the fake mechanism? Yeah.
Wait, why are you adding 2 to the OR?
Because that is just what the reaction does. Like, a fake mechanism here does not ask, why does chemistry happen? The why does the chemistry happen is all of this, the thinking through the curved arrows, why each step happens. The fake mechanism is a tool for us to just draw the product. Is that okay?
Yeah.
I know it feels a little bit like anti-knowledge to be like, don't think about that right now. But it's a tool for you to use alongside of this level of detail. And like just doing one or the other, I think will lead to struggles. Like if you only know the fake mechanism and don't know the actual mechanism, you can't do the mechanism questions. If you only know the mechanism and can't do a little fake mechanism, box problems are hard or take a long time. Okay, so yeah, I think that that's pretty much level 3 of working at this line reaction level, where now we kind of zoomed out a little bit. And so we're ready for the highest, kind of more background level of thinking. We need to think about what are the goals of this reaction. And I classify chemical goals as distinct bonds that need to be made or broken that the mechanism should accomplish. So what are the goals of this reaction? What's the purpose of this reaction? Why did some postdoc spend 6 years of their life doing this? Why are we making you learn this reaction? And plot twists, the purpose for most like reactions is to convert between functional groups. Like that is the whole thing. And then last thing is kind of generalizing, because typically we are going to give you the reaction with a specific molecule in mind and try to generalize it with like R groups on it, like the most abstract version it can be. So how would we categorize the purpose of this reaction? Does someone want to take a stab at it? Turn the aldehyde into acetal. Okay, so I'm gonna beef it up just a little bit to reversibly, because as we saw yesterday, not all of our reactions are reversible, and this, it's being reversible and something that we can put on and take off later is going to be a tool that is why we have this reaction. To reversibly interconvert between a ketone / aldehyde and an acetal. Great. So now let's start thinking about reaction goals of like make and break. So what are some bonds that need to be made? What are some bonds that need to be broken? Jerry?
You have to break the carbonyl double.
Yeah. And do we need to break the like pi bond or sigma bond or both? Both. Yeah, so this is another kind of intricacy. Is this oxygen one of these oxygens in the product? No. How do we know that? We know it because we've seen the mechanism. This oxygen we protonated was this OH, then we protonated again, became water. We kicked her off. So this oxygen has fully left the building, and like technically, again, organic chemists are lazy. We don't write balanced reactions a lot of the time. We kicked off a water as well. So that's a product that we just imply there. And so I can put that in parentheses just to be like.
Do we assume that it's always being water? That there's always water around?
Not always. So, like, I mean, this one we didn't need to have water in our reaction. We just needed some acid. So we could have had like sulfuric acid or something. But we created water. But some reactions are aqueous, and like that's why like all the solvent and reaction conditions are important for like the context of the reaction. In biochemistry, you assume everything's aqueous because we are made of water. Okay, so goals: break, and I'm gonna be like specific with the bonds. We're gonna break the sigma CO and pi CO from the carbonyl. And then, what bonds do we need to make? Yeah, sigma COs with that OET. And technically also we needed to break like the OH on the ethanol, the original one. But that to me feels like such a like acid base, like loose thing that it's not worth writing down in this, because if we write down like every bond that was made or broken in the whole scheme of things, it's going to take too long. But these are like main chemical goals can we now go back to the mechanism and see where did we accomplish these goals? So did we accomplish any of these goals in the first step? No, this was a setup step. Did we accomplish any of these goals in the second step?
Yes.
Yes, what did we do?
Or grow to
And we broke the PyCO and made a OET, sigma. So we got kind of like halfway there on our goals. So very like productive day. Now, in this, do we accomplish any of our goals explicitly? No. Lone pair push, did we accomplish any of our goals? Yeah, we did the other half of this red goal. We broke the sigma CO from our original carbonyl. Okay. This step, did we accomplish any of our goals? Yeah, we did our last make the OET bond, the sigma CO. So again, I think by thinking about these goals and making and breaking bonds, it gives more of a sense of purpose to the arrows. Like when we started this exercise and we were just going along step by step, we didn't have any idea of like the big picture. Like we were so in the weeds that it was hard to see kind of why all this is happening and to start to point out patterns. And I know at this point we've kind of beaten this horse to death of like, we did a lot on this, but do you see how like this process of analyzing reactions makes you think about it more? It makes you start to notice some patterns, make connections, and these are skills that you can apply to other reactions and other scenarios that you're going to see in the future. The last thing that I didn't write out was the generalization here. So we would just generalize this from the specific reaction given to like R groups. So I would say a ketone or aldehyde, I would do as like R on one side and an R or a hydrogen on the other side, ketone or aldehyde. We have ROH, and maybe I'll do R prime just because there are a lot of R's in the mix, and I'll say like R prime is from the alcohol. It's literally just like whatever you want. You could use just R again as long as you know to keep it straight. And then the product, we have two OR primes. So, again, my pitch. You do need to think about reactions at all of these different levels in order to answer all the different types of questions that we give you. So now, your task is going to be, for all of the other reactions in lecture, do this kind of process. Like, set aside some time and, like, go through, label the mechanistic logic, analyze the line reaction, make your fake mechanism. And to help you in studying, I have made a review sheet, which is the last page of the section notes. So for this, just like what we did, I have all of the steps listed out. I have a basic kind of line reaction here. And I also put like notes, like specific things to keep in mind. Like there are some reactions that only form certain products, or like these, there's a special note about like reacting with esters. But like essentially heed this warning of this is a trap. If you only use my review sheet and like work all the problems by like looking at this, when you get into the exam and you do not have my review sheet, you will be in trouble. But also like I wanted you to have some scaffolding and see an example of what you should be doing and what the important information is from those reactions. So I hope that this will be a helpful thing. The last note in this kind of larger organization is I've divided up all of the reactions from lecture into 3 families. So one family were the organometallic reactions, the carbanion reactions. These are about adding carbons to a carbonyl. Then we had the hydride equivalent reactions, adding hydrogens to a carbonyl. And then the last family were these reversible reactions that all go together. And again, by grouping them together, we are grouping together reactions that have similar steps and similar logic. Like the mechanism for these two is almost exactly the same, but you're replacing a boron with an aluminum. The mechanism for these is almost exactly the same, but you're replacing magnesium and lithium. Like that's it. These, there's a little bit more variation, but all of them are using those same few steps. Cool. Any questions? That's my TED talk. Yeah.
So, when you have the arrow, then what is the order of the substances on top of the arrow versus below the arrow? Like what order?
So if they can all be put in the same pot, it doesn't matter. If it's like on the arrow, you can write them above and below. You could write CH3OH like beside it. Typically, the convention is the main thing that's reacting you put up top, and then the solvent you put below. Like that. That's just common practice. But like we don't care. You could write them all on the same line. But if things are two distinct steps, you straight up have to write step 1, period, whatever, step 2, period, whatever. If you do not write the 1 and 2, it is wrong. Because without this, it is saying add a ketone aldehyde, add a Grignard, and acid all in one beaker. And like that is going to defeat your reaction. Like it's not going to go the way you want it to do because you're putting it all in one beaker. So you do have to list the 1 and 2. Yeah, totally. Other questions of like how to approach studying reactions? Do you feel like you have some tools to analyze?
Wait, sorry, can you repeat why this is a trap?
This is a trap because like it does all the hard work of studying the reaction. It does the like having to analyze a reaction, figure out what's going on, figure out what's important. Like the whole process that we just did here, if instead of doing it together, all I did was give you this, it's cheating you of learning it. Like you're still going to have to spend time with that reaction, learning all the steps and why it happens. And so it's kind of like, don't use this as a crutch. Like use this as an example for how to structure your like own review sheet, but like you're still going to have to do that legwork on your own. Yeah. Yeah.
So some of these, you mentioned the reversal. I noticed that some of them are kind of weighted in the arrows. How do we find that information? Like which one's favored? Or
So I believe in lecture the arrows were weighted.
okay.
Yeah.
And that's just a piece of information we should memorize.
It's not that important. Like it's yeah, in the hierarchy of information, it's lower. I don't think we're gonna ask you to kind of predict which side of the equilibrium, for this, in the same way that we were for like acid base, where we were doing like KQ. Yeah.
Wait, are we gonna have the thing where yesterday we had the energy diagram? There's one.
We're not gonna ask you to draw energy diagrams. The idea behind it, of like the kinetic versus thermodynamic product, you need to know the difference between those and the reaction conditions, which like here, that is just these two bullets of like if you react this with an enone at 0 degrees, it does the 1,2 product. 80 degrees, we do 1,4, and we're gonna be talking about that in a little bit. Yeah. Okay. This was kind of a lot of information. Let's take like a 2-minute break, stretch our legs, and then we'll come back and we'll lock in and talk about the carbanion equivalent reactions. If you came in late, here is the QR code for attendance again. 2-minute break. Shifa. Ashifa. It's always the emphasis for the Jasmine, though. What is your name? Don't tell me. Don't tell me.
You can come back.
Is it Grace? Ding dong. I didn't even need the first letter.
No, like I
Steven,
first, like,
Sandra.
2 weeks ago.
Okay.
Just like
Lily.
Yeah, oh, because
Is your name Gia?
happened or
Yeah, that's not your name. What's your name? Cecilia. I'm so sorry. Again, really bad with names.
there was a large period of time where it's like I would read all of
Jerry.
the books, and it's also there was like something on Amazon or something.
I have no. Wait, no.
But I feel like for some reason
First letter.
I read like that I had found it.
Cam? No. Call it. Ding dong. Okay. Now your name starts with a D. I know your name starts with a D. I keep wanting to say Dare, but that's not it. Dara. Dara. Nate. Oh gosh. Is her name Jessica? Work.
The beginning of last year, I got really like
Okay.
there was a period of time.
Stephanie and first letter. C. That's crazy. Second letter. Now I'm like Charlie. No. I love Charlie as a name though. Okay. C-H. Chelsea? Okay. Anna. Anna. Oh no. Izzy? That's your name? Yes. Okay. And Izzy is sitting by first letter? Ava? Okay, work. And Maddie? Ah! Hannah? No. First letter? Brand ambassador, Ozzy. Ding dong. I've been told that I should ask that you bring your drink for the section as. Where? And then. And then, what's her name? Nina. Work. Okay. Work.
What we have to memorize for the PH is what you put in the section notes, like all of it, or should we also know last piece that they like sprinkled in a few other...
Just those. Yeah, the other ones like are things to calculate from that, but just that is what we asked you about.
Okay.
Yes.
Because I felt like there was one or two like extra PKAs, but they gave them to us in the
Yes,
piece.
and we would give it to you on the exam. Those are the only ones we want you to memorize.
Thank you.
Yeah. Okay, let's jump back into things. So, let's talk about the family of reactions of carbanion equivalents. So the purpose of this family of reactions is often to add an alkyl group to a carbonyl. So we need to figure out how to make carbon-carbon bonds by adding an alkyl group to a carbonyl. And just by happenstance, we often form an alcohol as the product from that. So if you're looking at functional groups, it always is going to look like you're going from a like ketone or aldehyde to an alcohol. But that's not why we did it. The reason why we did it was to add an alkyl group. And I like the little like dog playing with the little dog toys of like an alkyl group and the carbonyl being like kiss. Like that's these reactions. So why don't we just deprotonate alkanes and make carbon nucleophiles? So what's the pK of this bad boy? 50-ish. So this is like, did you hear about the explosion that just happened in lab? That's the energy of this. We're going to try to avoid that. So that's why we need to use carbanion equivalents, things that are going to react like a carbon with a minus sign, but are not crazy. So these are going to be organometallic compounds. So typically we are used to seeing carbon in bonds with oxygen, right? And in this bond, who is the more electronegative element? Oxygen, so partial minus, partial positive. We are used to seeing carbon with a partial positive, but we want it to behave like carbon with a negative charge. So we need something that is less electronegative than carbon. And that's typically going to be a metal, which I just abbreviated metal here with M. And the ones that we use are magnesium and bromine together, or lithium or copper. Those are kind of our metal stand-ins. But in this kind of dipole situation, the electronegativity of carbon is 2.55, but most metals have electronegativity of less than 2. So in that dynamic, it's a partial minus and a partial positive, which is similar to this, like a negative charge and a positive, like almost ionic bond to E. I will say, this is just to give you vibes. We want you to actually draw the bond. We do not want you to draw a lone pair on carbon. So this is just, again, I'll put kind of parentheses around it, vibes. Now, first up, we have the Grignard reaction and the alkyl-lithium reactions. So if we want to add an R group to a ketone or aldehyde, we either add RMGBr or RLI, and we add it in a diethyl ether solvent. Now, diethyl ether ET2O looks like this, like a little ethyl group on each side. And I always just think of it as like a little auction bat, like flapping its wings. And Grignard vaguely sounds like a vampire name, and so that's how I remembered it, and like it just stuck that way. And we talked about it briefly, but the main solvents that you see in lecture 3 to have, you'll either have diethyl ether as the solvent, or you'll have an alcohol as a solvent. And you need to know which reactions need ether solvents or alcohol solvents based on like the line reaction that's presented. So it's just one of the other kind of pieces of information to fold in. Now, diethyl ether does not at all participate in the reaction. She is just the medium within which the reaction is taking place. Like, if we try to do this without diethyl ether, what it would be, this is going to be like an oil, kind of thick substance, and this is going to be a solid. And so if we just put a solid on an oil, is it going to mix very well? No. So that's why we do it all in diethyl ether, which is a liquid, but it's not aqueous. Cool. So the first step is going to add our R group, and then for each of the steps we have to do, or for each of the reactions we have to do a second step acid workup. And again, we have to explicitly write step 2. It's an acid workup. Acid workup can be a bunch of different things. Some classes, they prefer students to write like H2SO4, like acid, like a very specific acid. You could do HCl or H3O+. You could even do an acid workup just by adding water to a reaction sometimes. Because this is something we don't really care about, and we don't care about you knowing, you could just write H+ workup, and it's kind of a blanket statement that covers it all. It's also the thing of like, don't cheese the exams, but like on the box problems, if we asked you for reagents, sometimes you can just get a point by putting H+ workup, if that's one of them. Like, hey, get your points however you can. So let's talk about how do we make these reagents in order to use them for the reaction. So the reagents here always start as an alkyl halide. So if we have an alkyl halide, we can add magnesium in diethyl ether, and it makes our Grignard reagent. Now, this superscript 0 is just indicating that we have elemental magnesium, like solid magnesium, as opposed to like magnesium 2+, which is like an ion in an aqueous solution. Now, our Grignard reagent, when we make her, she is a strong base. So one thing I think that I saw some confusion about during the lecture notes was Logan had indicated out here, like if there was like a water present, this can just go grab hydrogen, and then you have R with the H added. I did OH too, sorry, but I just mean OH, and then you have OH minus. So essentially, the Grignard can go and just deprotonate a water, and then it's not going to do the reaction we want it to do. This is an unwanted side reaction. And honestly, like Grignards in the lab are kind of finicky. Like, did y'all do a Grignard this week? Is that, I truly have no idea what y'all do in lab.
Spinach chromatography.
Fun.
Column chromatography.
Cool. I don't like lab. I don't like lab. I like chemistry as like a mental exercise. I don't care that it exists in the real world. No, it's like Sudoku or something. Like, so that's the thing. Don't be confused. Like, this is a unwanted side reaction, but if you try to do it in lab, it can be so finicky that like I did my first organic chemistry classes in Georgia where it's quite humid. And if it's too humid on a day and like the lab is not well like ventilated, you can't do a Grignard because it's going to react with the moisture in the air. Like you can have like parts per million of water and it's going to disrupt your Grignard because the Grignard is so basic. And so that's why we need an ether solvent. It's also why if you put an alcohol, methanol, it's just going to react with the alcohol and deprotonate it rather than do what we want it to do. And then if we want to create alkyl lithium, also in diethyl ether, we just add 2 equivalents of lithium. For these, you do not need to know any mechanism, mostly because like metal stuff, we don't really get into. We want to be able to use these reagents, but we care more about how it affects things with carbon rather than just the intricacies of metals. I don't know. So let's talk about the actual mechanism for both these reactions. The mechanism is exactly the same. So you go from your R, like carbon metal bond, this sigma bond, and the electrons from that go and attack the carbonyl and push up to the oxygen. So we have, again, with our mechanistic logic, the sigma CM bond, and where M here is our MgBr or our lithium, and that is the nucleophile attacking carbonyl electrophile. When this happens, like imagine this carbon of the R group is in a relationship with the metal, and the carbon says, I'm going to take the children and I'm going to marry someone else now. And this metal is just like, Like, it literally, we say it like sloughs off in the reaction. Like, goodbye, I guess. We don't care about her. And often we don't even, like, draw it because it's not important. It's not, like, she's not the main character. She's a side character. She really is. So, once we do our reaction, we have created a new sigma bond to R on this carbon that was in the carbonyl. And now we have a negative charge. And so the second step is we're just going to protonate it to neutralize. And that's our acid workup step. So exact same reaction for both of them. Cool. Any questions on Grignard or alkylithium so far?
It doesn't have to be diethyl like oxide though, right? Then
The diethyl ether?
yeah, diethyl ether.
You could
Like,
technically use other ethers. Use diethyl ether. Just because it's the one that's on all the problem sets, it's the one that we're going to put on the answer keys. So just to make things easier, do that. If you used another ether and it was correct, we would give you points. But if you put an alcohol, we will take points away. Yeah. Yeah.
How do you know which reagent to use?
Like which R group? Or like which one between these?
Yeah, do you use alkylithium or?
So right now, these are 100% equivalent. So like, why are we teaching you two reactions? Very valid question. She's going to come back over here with Eno and stuff. But right now, for just reacting with a ketone or aldehyde, these are 100% equivalent. There's no reason to do one over the other. Both would be valid on answer keys. Yeah.
Sorry. So in the
No.
long synthesis reaction, I saw that there was like a step where you guys were like the reagent prep was like in part of that synthesis part. I think like they.
Yeah, so, okay. If, let's say you were doing a reaction where you are already starting with a carbonyl and you want to add carbons to it, you can supply a Grignard reagent. Like, that is totally fine. But let's say, like, you wanted to turn a starting molecule into this actual Grignard. So, like, in this, like, first one that I showed, you don't know this reaction here, but it essentially adds a bromine onto the benzene. And here, this is the thing that we have, and we want to get it to be able to react. So we want to be able to use this line reaction to turn it into a Grignard reagent, which then we can have react with a carbonyl. So, yes, that's where it comes in. That's why those line reactions, even though you don't need the mechanism for them, are important and will be used in box problems and synthesis. Great question. So, okay. One variant of this reaction is instead of reacting with ketones or aldehydes, these also react with esters. Now, especially for exam 1, the first thing that I want you to think when you see or hear an ester is double addition to ester. It needs to be automatic, almost like Pavlovian conditioning. So can we try our practice here where I say ester and you say double addition to ester? Ester. Double addition to ester. Ester. I have a latte ready for ester. Double addition to ester. It needs to be that immediate because if you see an ester on the exam, you're probably doing a double addition, for at least for exam 1. So if we have an ester and we try either of these reactions, what we do is we add 2 of our R groups, double addition to the ester. So the first step is exactly the same, and like the carbon metal bond attacks, and then we get to this intermediate. But this intermediate is different from if we just attacked a ketone or aldehyde here. So in this ketone or aldehyde, all of these are bonds to carbon, or like sometimes it's a bond to hydrogen. But those sigma bonds of carbon to carbon, carbon to hydrogen are hard to break. We need a cinematic lone pair push if we're going to break one of those. Or actually, we need something stronger than a lone pair push. We are not going to kick off carbons with a lone pair push. Breaking carbons is like intense. So up here though, we have an OET. And an OET we can kick off as OET minus. And like if we are kicking off an O minus versus like let's say a CH3 minus, neither of them are particularly happy, but which one's going to be more stable of the two options that we could kick off? The OET minus, exactly. So we are going to do our cinematic lone pair push and then break this sigma CO bond. And then we are back to a ketone. So we are still in this part of the reaction where we have our Grignard present. And so if we regenerate a ketone, it's going to react again. So another equivalent of our carbon metal bond is going to go and attack and push up. Now we have this intermediate where we've added 2 R groups and we have an O minus. Then we do our acid workup step, same as before, where we just protonate and neutralize it. So that is the one variant of doing these reactions with an ester. We're going to have our double addition to esters.
What if we just want to do it once? What if we just
Y'all don't have a
wanna-
way of doing that. Yeah. Mm-hmm. You would need to first convert it to a ketone or aldehyde and then do it once, which you will learn tools of how to do that eventually. Cool. So let's talk about the question that Dara brought up of like, why do we have two of these? Like, why did we teach you two reactions that do the exact same thing? And it's because it differs in how they react with enones. So our second kind of big idea here is an enone, which is a combination of an alkene and a ketone, that here, each of them have p orbitals. They're all next to each other. So they have what between it? Resonance, electron delocalization. So our big idea here is enones actually have two electrophilic sites. So like a carbonyl only has one electrophilic site normally, and that is one of our sites in the enone, but also the end of the double bond here, like the far side away from the carbonyl, is also going to be an electrophilic site. And we have this kind of idiosyncratic naming system for enones, where we start at the oxygen and count 1, 2, 3, 4. Now that's different from nomenclature, where nomenclature we number carbons instead of like oxygens, but here it's just a convention that stuck around. I'm so sorry. So we say that if we are attacking at the base of the carbonyl, that is addition at the 1, 2 site, and you would do like 1, 2. So we would call it 1, 2 addition if we're attacking the carbonyl site. But if we attack here at carbon 4, we call that 1, 4 addition. It's also called conjugate addition. Now, one thing that we are not testing you on, but it does appear in the MCAT, and so I wanted to just flag it so that you've seen the term. We say nucleophiles that add at the 1, 2 position are called hard nucleophiles, whereas nucleophiles that add at the 1, 4 position are soft nucleophiles. Again, we are never going to use the terminologies in the class ever again. We're never going to ask you about that, but just in case you see hard or soft nucleophiles in the future with enones, this is what it's talking about. So let's talk about our different ways of adding an R group. So first off up here, if we did our Grignard, so our R-MgBr in diethyl ether with an acid workup, the Grignard reaction is unselective. So it is going to equally likely add at the 1, 2 position and add at the 1, 4 position. Do you think that we like reactions that are unselective? No. So Grignards, for the most part, you are almost exclusively going to use with just basic ketones, aldehydes. You will not really use them with enones because it's not selective. Okay, so then our second version that we learn, alkylithium, this is a reaction that is one of those hard nucleophiles that only will add 1, 2. So it is only going to react like it would react with a ketone or aldehyde at the base of that carbonyl, and it is selective. It will never do 1, 4 addition. Okay, great. So we have a way of selecting for that 1, 2 product only. So now we need actually a third organometallic reaction in order to get something that's selective for 1, 4. And this is that Gilman reaction that was kind of introduced at like the bottom of a page and then on the next page. But again, at that point in the lecture, y'all were already too far gone. I was like, we'll just get to it in section. So there are two ways that you can write this reagent, and I'm going to tell you that there's one that's a bit more preferred. So the one, when you first saw this in reaction in lecture, it would be alkylithium, and then you would add in a copper halogen, like CuBr, and then Et2O. And then second step is an H+ workup. That is valid. It's like you're doing the lithium and sprinkling in copper bromine, and that is going to make it add 1, 4. The better way of writing it, in my opinion, because it's a little bit more condensed, and also because it is what all your problem sets and answer keys say, instead of writing out RLI and CuBr, you are going to write R2CuLi. So essentially, if you have your alkylithium and copper halogen in a mixture, it is going to form this complex. This complex looks weird. We're never going to ask you to draw this out. I don't think that we are ever going to ask you a reaction mechanism for this. So Logan showed you a simplified mechanism for the Gilman reaction, but it's actually it's kind of not true. Like copper kind of does this complex with the carbonyl that's a little bit beyond y'all's pay grade at this point. And so I don't think that we're ever going to ask you a mechanism for the Gilman. At least that's been our policy in the past. It's only a line reaction for like box problems and synthesis. So I think given that, writing R2CuLi is going to be the way to go here. So like let's say you wanted to add a methyl. You would do Me2CuLi and Et2O, and that's the reagents you would use. If you wanted to add a phenyl, you would write PH2CuLi, and it would add a pH here. What if we wanted to go from this initial enone to this product? Can you take a minute and try to figure out how you would write the reagent to do that? So we would have something with Et2O and H plus workup. So for this, I've drawn out the kind of 1, 2, 3, 4 of our conjugate system, and we know we want it to add at the 1, 4 position. So I'm going to draw a little squiggle here, because that's where we've added something. So we need these carbons, these 3 carbons. And so the way I would draw this is we have those 3 carbons, this 2 of them, CuLi. Or, yeah, CuLi. Yeah, that's it. And again, you can use like a parentheses. Like if you added, like let's say, whatever, you could do this 2 of these on CuLi, and that would be valid to put for the reaction. Questions about this notation?
Is there an official name for this or an abbreviation? Like there was phenol and methyl.
Like is there a name for this compound, or like this compound?
Yeah, that Y.
So we call the class of compounds organocuprates, cuprate referring to copper there. This would be like diisopropyl or lithium diisopropyl cuprate, but like we're never gonna ask you to name that. Yeah.
But we can't shorten it with like ISO or something the same way, or like some shortening the same way we do ET.
Yeah.
Yes. So you could do like isopropyl to CuLi. The only thing, yeah, I think that would work here. With more complicated ones, though, of like if you had something like this, then there wouldn't be really an abbreviation that you could do that would be easy. So just drawing the structure is the way to go.
And the thing in the bracket has 4 carbons. whereas
Nope,
there's-
only 3. 1, 2, 3.
Oh, that's just.
And then this cuts off. These are kind of bonded to the copper.
Right. So the bracket has to cut off that 4.
Exactly. Mm-hmm. Good questions. Cool. Now, the Gilman reaction here, this organocuprates, it is less reactive than a Grignard or alkylithium. And so, specifically, it will only react with enones. It's not going to react with esters. It's not going to react with normal ketone aldehydes. So the only context to use this is this version where we're specifically trying to do 1,4. But again, this is kind of thinking on the scale of synthesis, line reactions, of like the higher order thinking. Yeah.
Why is there a 2 after the structure? Did you remember 1 of the reaction?
After,
Relationship at the bottom.
like this, why is there 2? Because when you put the alkylithium and copper bromine together, it creates a complex where there are actually 2 R groups. So like it's because copper likes to have a certain number of bonding partners, and like it's just going to form this. Yeah. Yeah, Colin.
Are we specific about the actual mechanism for why it's selective?
No. Like, again, so the why it's selective, getting into metal stuff, is a little beyond y'all's pay grade now. If you take, like, inorganic chemistry, you'll learn some of that. But, like, you just need to know that it is 1,4. Yeah. Cool. So, let's actually see what a mechanism, though, for a 1,4 addition would be. Because I told you the Gilman, we're probably not going to ask you a mechanism because it's a little bit more complicated. But conjugate addition is something that you do need to know the mechanism for. And the one that was given to you in class is a thiolate. So, a thiolate is like a negatively charged version of, like, a thiol. So what we're going to have here is we are going to have a lone pair on our thiolate go up and attack the carbon at the 1,4 position. And then we are going to push all the way up to the carbonyl oxygen with 2 arrows. So we are going to move the electrons in this double bond, make a new double bond here in the middle, and then move the electrons in this pi bond up to the oxygen. And so it kind of combines almost the idea of like resonance arrows with a nucleophile electrophile arrow, because we said it's delocalized. There's resonance there. So our product that we get out of that, we now have an O- at the top. We have a double bond created in this new spot. And then at the 4 position, we've added our S and our ethyl. So now, at this point, we do a step that looks a little bit weird. But if we think about it, if we're going from here to here, we definitely need to reform our carbonyl, right? But then the other thing that's kind of sneaky that we have to do is look at this carbon right here. That's going to be this carbon over here, correct? How many hydrogens are on the carbon in the product? How many hydrogens are on the one in our intermediate? So we know that we have to add a hydrogen there. So what we are going to do is we are going to push down from the O-, and then have our double bond go and grab a hydrogen. And this time, it's going to be from our solvent, our HOET alcohol solvent. So this is a reaction where the solvent is playing a role in the reaction. It is supplying a hydrogen, whereas like diethyl ether doesn't play a role in the reaction. And so that's why it's important to know which reactions have alcohol solvents versus ether solvents. Okay, so then when we do that, that's going to give us our product over here. So there's a special name for this step that Logan did not use, but it's going to come back in lecture 5. So you're going to see it on Tuesday. So I'm just going to go ahead and give you the language for it so you can help summarize those steps, get it into like summarizing the mechanistic logic. So this is called an alpha protonation. Because when we have a carbonyl, we call the position right next to it on either side the alpha position. And then the position 2 away from it's the beta position. And again, that's going to be explicitly covered in lecture at another point, but just so that you have a name for it, because at the end of the day, this is an acid-base reaction. This is a protonation, right? It's one extra step than what you would normally see for a protonation. And so it's just a different flavor of protonation. Okay, so with that, we've covered pretty much all the content in the carbanion family. So I want you to do some practice problems here. So I hope these pages are right. I'm not sure if I fully updated them. But you can either hunt them down in the problem set, or you can work them on here. And then I believe this is one that I just made. So this is one that isn't in the problem set, but I think would be good practice. For this first one, you're going to straight up regurgitate arrows. Like, go through, just draw the mechanism of a Grignard. Then, these are all some box problems, where you're going to have to identify which reaction to use and the reagents to supply the transformation. So I'm going to give you about 3 minutes to work on it. Just do what you can, and then we'll come back as a group and we'll do all of them together. Cecilia. Cool. Yeah.
For the external contamination, why doesn't the oxygen just protonate? Why do we protonate from the carbon?
Sorry, what is the question?
Like, to balance the structure, so there's no charge, could you protonate on the oxygen as well? Like,
So you could protonate on the oxygen here, and then you'd wind up with a structure that's OH here. So that's a structure that's a compound functional group called an enol. And enols very rapidly interconvert back to carbonyls because they are very reactively equivalent. And we're going to talk about them in lecture 10. So she's coming back later, again, asking good questions. I don't have a good answer for you other than you'll see later. Yeah. Stephen, Grace, Jasmine, Cecilia, Garth, Jerry, Dara, Dara, Which one?
Dara.
Dar. Okay. Colin. Nate. Jessica. No, don't say anything. C. Chelsea. Stephanie. Anna. Okay. Lily. Oh. June. Bert. Matt. Sandra. Ozzy. Izzy. Ozzy, Izzy. Cool. Nina. Ava. Woo! Oh.
When you were speaking about the E, and then you said it word that the ET is that because we're likely going to use it as an intermediate in like adding nitrogen or something?
Not exactly.
Just later.
Just later. I mean, I think actually the best argument that I could give you right now is like this product molecule with a CO double bond has a lower bond enthalpy. Like it's more stable as a product than enol is, and enol is less stable. So I think maybe that's a good answer for now. Okay. So, you have not had time to do all of them, but we're going to start talking. So, the first one should be pretty kind of like straightforward. We write out our Grignard. We do a arrow from the bond attacking the carbonyl, push up. Now we have an O-. We've added our R group, which is an ethyl here. Then we do our acid workup, where it just grabs an H+. Done. So the mechanism for these, so much better than acetal. That's why I did the analysis example with y'all with the acetal, because that's the scary long one. Okay, so what functional group do we have in this reaction? And what's the first thing that you should think when you think about esters? Double addition. So do we see anything in our product where it looks like 2 of something has been added to the same carbon? Yeah, 2 what? 2 methyls. So, does it matter if we use, or like Grignard or alkyl lithium? No, we could use either one. So I'm just going to arbitrarily use lithium. So methyl lithium, Et2O. If you want to be like that girl, you could do 2 equivalents to just say, hey, we're using it twice. And I know that we're using it twice. If you don't include that, we'll still give you full points. Some classes are real picky. Some classes are like, actually, we need 3.5 equivalents of blah, blah, blah. No, that's not us. Again, in some ways, Harvard is much worse than other schools. In other ways, it's a lot nicer. Like, I think there's less, like, BS work that we give you in terms of, like, the chemistry that you have to know. And then we just have the H+ workup. So, that's all this box problem was. Now, for this second box problem, we have an enone. It looks like we're adding things at the 1,2 position and the 1,4 position. So what did we add at the 1,2 position? We added an ethyl at the 1,2 position, because remember, it's 1,2 at the base of the carbonyl. And then what did we add at the 1,4 position? A phenyl. Okay. Then we need to clock, after we've done this analysis, okay, to add things 1,2, we need to use a lithium. To add things 1,4, what metal do we use? Copper. Okay, so now the question becomes, which do we do first? What do people think? Can you do a can you do a peace sign if you think that we should add 1, 2 first and add lithium? And then can you do like like crossing the arms if you think we should add 1, 4 first? So peace sign for 1, 2 first, crossing arms for 1, 4 first. Okay. Okay. So a lot of people are saying 1, 2 first, so let's try it. So if we add 1, 2 first, let's do ethyl lithium, Et2O, and an H+ workup. Our intermediate that we'd get out of this, and we get no points for writing the intermediate, but it's sometimes helpful. We would have our HO over here, and then we've added our ET, and then we still have this double bond. And now, this. Do we have a carbonyl anymore? Do we have an enone anymore? So can we do anything with a Grignard or alkylithium? No. This is now an alcohol and an alkene because they're separated by, this is an sp3 hybridized carbon. So like there's no resonance anymore. And you don't know the reactions of alcohols or alkenes, so this is dead in the water. I'm so sorry. So what that means instead, we are just going to shift it down. Those are going to be steps 3 and 4. And first we're going to add 1, 2. So we're going to add phenyl 2 CuLi. I think I misspoke. The first one we're going to do is adding 1, 4. Et2O with an H+ workup. So after steps 1 and 2, we're going to wind up with this bad boy. And now do you see how after we've done this 1, 4 addition, we still have a carbonyl? So we can still do like Grignard, alkylithium, whatevers. And actually, because we did this first, do we have to use lithium for step 3, or could we also use a Grignard? Is she an enone anymore? No, she's just a ketone, so we could use either one. But here, steps 3 and 4 will get us to our product. Okay, last one down here. This one's tricky. Yeah.
Question about that one. So for the when we added the phthalate, we used ethanol
Mm-hmm.
as a solvent, the ethyl ether.
Yep.
Because it has that extra hydrogen.
That we're gonna need for the reaction. Yeah.
Would we be able to do that for the first step or more?
Absolutely not. Because remember what I said about the humidity in Georgia? If there's anything like water, or like remember alcohols have a similar pKa to water, the Grignard or alkylithium is just going to deprotonate the alcohol or water. And so that's why we have to do the H+ workup as a separate step. That's exactly the reason.
And then if we do the H+ workup as step 2, how do we do step 3?
How do we what?
How do we do step 3? Like, do we have to like, get all the water out? Or how does...
See, that's why I'm like, it's a mental exercise. Like in lab, they probably need to dry it out. So you'd probably sprinkle in a compound that absorbs all the water, like some sulfur thing. And then, yeah, like it's the thing. I just aggressively don't care. But they have to do something in the lab to get it out. Yeah. So last one's kind of hard here. And if y'all are okay with it, I'm probably going to go like 3 minutes over. Because I want to give like a very quick intro to hydrides. We're not going to do much with it, but I want to explain this problem and then do an intro to hydrides. I'll try to be quick. So, what functional groups do we have in the starting material?
Alkyl halide.
We have an alkyl halide. What else? Aromatic ring, arene. What else? Ether. Great. Look at y'all. Y'all studied. Okay. So, do we know any reactions with ethers? Like where ethers are doing the reacting? No. Do we know any arene reactions? No. Do we know any alkyl halide reactions? Truly only like turning it into a Grignard or alkylithium. So let's just do that. We literally like fancy restaurant like shaving in the cheese. We shave in the magnesium. Yeah. We add in elemental magnesium and diethyl ether because that's the only thing we know how to do. So if you see an alkyl halide on the exam, plot twist, you're probably going to turn it into a Grignard or alkylithium. So, okay, so now we have a Grignard reagent, and let's look at our product. So our product, it looks like we have an alcohol, and I would say like all of this, blah, 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 I know where she came from. I've sourced it. But then we have on the outside a carbon here that was not there before. So we have to supply that carbon because where did she come from? And the other thing to notice, she has 2 hydrogens. So what's a carbonyl version of this? Because we know our Grignards and alkylithiums attack carbonyls. Well, it would be a carbon. Hello. There we go. It would be a carbon with 2 hydrogens. And we'd have a carbonyl in its place. And you can imagine it being literally like, I'll rotate it just so you can see, blanc. So a Grignard attacked this carbonyl and it made this product. And so this one is kind of weird because normally you're used to, at this point, putting the MgBr compound, the Grignard reagent, on the arrow and then having the carbonyl on the left side. But now we're saying, hey, we could also have the Grignard on the left side and we can put the carbonyl on the arrow. And that is totally fine. So here you would supply the carbonyl and the diethyl ether and then do an H+ workup. Now I know that was kind of quick. I'll answer questions afterwards, but I'm going to very, very briefly do the hydride rundown. Hydride family reactions. So this is the second big family here, where the purpose is to add a hydrogen to a carbonyl. So we could use NaH, and it is a strong base, but it's a poor nucleophile. So if we wanted it to attack a carbonyl, it's simply just not going to be nucleophilic enough to do that. So we need something that acts like this. Some people are also like, okay, we need to add an H. Why don't we just use H+? H+, she has no electrons. How can she be a nucleophile? What would she donate? No. Sorry. That was a disgust reaction. That was a little bit strong. So again, like the carbanion equivalents, we need something that acts like H- but is not H-. And our solution here is, remember, normally CH, we have a partial negative, partial positive, because the carbon's more electronegative. We need something that reverses that. And so we have it bond with like group 3 elements. So typically it's either boron or aluminum. And comparing the pKa's, the hydrogen is going to be more electronegative than the boron or the aluminum. So we have a partial minus here, partial plus here. It's going to react like H-, very similar to what we saw with carbanion. So our 2 flavors that we have are lithium aluminum hydride and sodium borohydride. And there are a lot of similarities and some key differences between them. So to talk about those, I made a little table. So I give these two, they're brothers in my head, and I give them like little metaphor names. So I call it lithium aluminum hydride toxic masculinity. Why do I call it that? She's very reactive. She will pop off. She's quick to anger, very roid rage. She reacts with everything. She will react with ketones, aldehydes, esters, and more things that you don't even know about yet, that you'll learn later. So she reacts with everything, very reactive, is quick to pop off. Whereas sodium borohydride, soft boy, so sweet, mild reaction conditions. Ooh. It will only react with ketones, aldehydes, will not react with esters. And also, because of this mild conditions, we are able to do sodium borohydride all in one step. So do you remember before we were talking about like why don't we use alcohol solvents with Grignards? Because they're too basic, too reactive. Well, here, because it's mild, we can just use methanol all in one step. Also sweet, harmony, coexist. Whereas lithium aluminum hydride, roid rage. If you put acid or alcohol with lithium aluminum hydride, it will just do acid-based stuff and will not do the reaction you want it to. I've written down the mechanism here, but I just wanted to kind of clarify that. Last thing is, what if these react with enones? Neither of them are selective. These are not good reactions with enones unless we pull our little Uno reverse card. If we sprinkle in CeCl3 into our sodium borohydride soft boy, it will only do 1 and 2. So like normally sodium borohydride to an enone is going to give us a mix, but if we sprinkle in CeCl3, only 1, 2. Sorry? Hard nucleophile. It becomes a hard nucleophile. Exactly. That's all I went over. Thank you for bearing with me. I'll stick around for questions. Thank you for coming to section. You've got this. I believe in you. See you tomorrow. Scary announcement tonight.
What is the scary announcement?
I will send out a scary, it's just kind of an intense announcement on Canvas about the practice exams. It's not actually bad, but it's going to have recommendations on how to like study and like approach the practice exams.